Alright, so we are to 3.2. This is chapter 3, section 2. This is Managerial Economics 14, correct?
14, yes.
14. So 3.2 is unconstrained. Unconstrained optimization. And remember, unconstrained optimization is we could choose any value from the choice variable as we wish, as we will do best. So, first of all, what's the basic formula? This is on page 85. Net benefit equals, let's see how we call it, total benefit minus total cost. Remember, total cost is economic cost. It includes all costs. Ideally, we should also be including for economic decisions also opportunity costs. So, what do we have here? We have here what we call the next concept is that of a typical curve. Usually, benefits or revenues are represented by curves, and usually costs are represented by curves. Usually, for a benefit, which is the curve, the benefit is usually revenue. And revenue is simply quantity times price. For most businesses in the real world, the price is usually fixed. You cannot affect the market with your quantity, alright? For example, for Bulgaria, which produces barely 50,000 barrels of oil, which is of course nothing, right? We just take the world price of oil as it is, and that's it. Similarly for wheat. We just produce very little wheat, we can sell it, and we just watch and observe the world price, and we take the world price as it is. So, for most businesses, you take the price of the market, whatever it is. Remember how we called this from lecture 1?
The setter and the taker?
Yes, price takers. Price takers. Price taker. Someone that is not a price taker, an example of someone who is not a price taker, which is a company? Saudi Aramco, right. Saudi Aramco is not a price taker, it's a price maker. Itself, it can choose exactly how much to produce and can affect world price of its own output. So, for price taker, the price is constant. And if the price is constant, it simply means that total benefit is quantity times price. So, is a linear function of quantity. In other words, price is just a simple constant, okay? We just say equals to constant times quantity. How do we represent it on the chart? Very simple. Straight line through the origin. So this represents here the total, and we're going to have total benefit, total cost, alright? And this here is the choice variable. How much wheat the farmer would or should produce. And the cost is fairly straightforward. It is just a straight line up. It is line because the relationship is linear. In other words, you double the quantity, you double the revenue. You triple the quantity, you triple the revenue. You quadruple the quantity, quadruple the revenue. So this is total benefit, alright? Now, about cost. Cost usually is represented beginning from 0, but sometimes cost is represented to begin from some fixed value. In other words, sometimes businesses will actually have, let's use now a nicer color, fixed costs. Fixed costs. So, fixed cost simply means that the business incurs the cost whether it produces or it doesn't produce. A different way of saying it is that the cost is the same no matter what the quantity is. In other words, this is a fixed cost and it will not affect. For the university, what is a fixed cost?
Building.
The building is fairly fixed cost. Lighting is mostly fixed cost. The most fixed of all is just heating. It will be cooled or heated whether you have 2 or 20 or 200 students, right? Sometimes, even if you don't have any students, it is still optimal to cool it throughout the day and throughout the night, because otherwise, you know, if you let it cool too much or heat, then it becomes suboptimal to, you know, bring it back to normal, all right? Just like when you leave for 3 days your home, you don't turn on and off your refrigerator, right? Something like that. Anyway, so sometimes you get fixed costs, and from this fixed cost, usually costs rise, and they rise. Now, what I'm looking here is I intentionally modified. Let's plug in. Let's zoom in on this upper one here. So let's zoom in on this one, the above chart only.
Okay.
Is it zooming good?
Yep.
All right. So what I am actually doing is modifying this particular chart. And I'm actually drawing the cost, and the cost we can draw is somehow we can draw it upward, and sometimes we can draw it downward, but it's not really downward. The correct words are convex and concave. The direction is always up, but the question is, what is the curvature? So let's kind of clarify a little bit. So we have, let's say, some costs like total benefits, like this. In other words, early on, costs rise a lot, okay? Early on, costs rise a lot. In other words, we got a second, third, fourth student, we got to hire a second professor, a third professor, we got to heat, we got to cool, we begin to incur quite a few costs. Now, in other words, the fixed cost was that of the building. Now, we got 3 or 4 students, we got to get a couple of professors, you know. As you add more and more students, you need a little bit more courses. Well, from one point on, costs will rise fairly little. So, from one point on, costs will be very low. When I say low, I mean marginal cost will be low. An extra student, in other words, what I'm drawing here is student 1, student 2, student 3 are extremely expensive because you gotta hire the professors, you gotta hire the administrators, you gotta feed an army of supporting personnel, right? But now that we got 4, 5, or 8 students, suddenly each new student is cheap, right? Right? Meaning the marginal cost is minimal. So early on it is very steep, the cost curve. Early on is very steep. Later on, when we're moving towards some sort of optimality, it is relatively flat, means we can add more and more and more students and it costs our very little. And then at some point it begins to cost a lot again. Why would it cost a lot again?
Because of the resources.
Yeah, now we need extra rooms. In other words, we may actually need a brand new building, actually, university. So that building, you have to allocate the capital cost of it appropriately. So if you're going to have a payback period of 20 years, it's going to cost, let's say, $10 million, then, you know, $500,000, you have to budget. You have to allocate that cost, even though it's a, you know, again, fixed cost, but we know with planning it's a little tricky. Anyway, you have to factor in that cost. A different way to think about it is, oh, we can have extra 100 students or extra 50 students. We're going to rent the building next door. So there's a little other college over here, technology and whatnot college, right? And the university will have to pay them a big chunk of money for every night to reserve those rooms for the night. In other words, once you're beyond optimality, optimality is not optimal solution. It simply means relatively low marginal cost for an extra student. Suddenly, from a certain point on, students begin to be very expensive again. Very expensive again. Alright? So this is total cost. And now I'm drawing total cost as what is known as an S-curve. S-curve. In other words, very early on, the costs are steep, meaning the marginal cost is high. Then, anywhere, let's say for our program, between 10 and maybe all the way to 50 or 60 students, maybe even 80 students, the marginal cost is relatively small, and then well over 100 students. Now we need a new building, we need a whole bunch of more professors, you need a whole bunch of other things. Suddenly, the cost steepens again. And when I say cost steepens, cost flattens, I always mean marginal cost steepens, marginal cost flattens. And this is total cost. So, what is marginal cost? What is marginal cost graphically? Well, for the first guy, the first cost is zero. So when you have zero, okay, let's just say this is it. We have some fixed cost. So for the first one, this is the marginal cost, all right? For the second one, this is the second marginal cost, all right? Are you zooming in nicely in there? Zoom in. For the third one, again, I'm dotting in here, like this. For the next one, I'm dotting in here. For the next one, I do the same thing here. So, I can now begin to draw something like this particular piece. We just call it marginal cost 1. This is the marginal cost of the first user. Sorry, the first, in this particular case, student. This second piece will be marginal cost 2. Marginal cost 2 will simply mean the cost to teach an extra student. Alright? Then this will be marginal cost 3. So, the point is that early on, the curve is steep and the marginal cost is high. Later on, you have somewhere over here, the curve is flat and the marginal cost is relatively small. Relatively small. We call it next to nothing, right? And then very later on, next student begins to cost an awful lot. Like this next student actually could cost you, so this is the next marginal. Maybe this will be marginal cost of, let's say, student 80, and this is the marginal cost of student 81. I'm just illustrating. Now, I'm doing a little trick here. I'm going all the way quite a few chapters ahead on cost and marginal cost, alright? I'm just developing it anyway because we'll have to anyway. So it's going to save me some time over there. So, this is the marginal cost. In other words, the slope of the curve determines the marginal cost. The slope of the curve. Steep slope means high marginal costs, and flat or relatively flattish slope means relatively low marginal cost. In other words, early on marginal cost is high, but slows down and then reaccelerates again. Alright? Is that fairly clear? Now, this, in other words, the marginal cost is represented by the steepness of the curve. Alright? Now, what about this one here, which is the total benefit? Can we say that the marginal benefit also depends on the slope of this curve here? And the answer is yes, certainly. 1 unit here gives you that much. 1 unit here gives you that much. 1 unit here gives you that much. Turns out that the marginal benefit is constant. Constant. In other words, the marginal benefit of the first unit is equal to the marginal benefit of the second unit, is equal to the marginal benefit of the third unit. So we say MB3, M marginal benefit 4, marginal benefit 5. Over here I'll do marginal benefit K. And in this particular case, I can write, because total benefit is equal Q times P, where the price is constant, it follows from here that marginal benefit of the kth product is equal marginal benefit of the nth product is equal to what? No. P to P. To P. Alright, let's, apparently some people don't see it. Let's clarify this. So, marginal, let's write this out. Marginal benefit of, let's say, the 7th element. This is number 7, alright? Is equal to total benefit of 7, correct? Minus total benefit of, you're asleep? 6 of 6. In other words, the marginal benefit of the 7th element is what you get for 7 minus what you get for 6. Alright? So, this is equal. What is total benefit for 7? Alright, it is 7 times P minus the total benefit for 6 is 6 times P, and now you appear to be waking up, right? So it turns out to be P, alright? Well, I can now derive the general MB of K. For any K, when you have a price taker, becomes TB of K minus TB of K minus 1 is equal to K times P minus K minus 1 times P. And when you cancel out KP with KP, you know what's KP? Krassimir Petrov, that's my initials. Alright? You get only P. Alright? So, the derivation is that the marginal benefit for any quantity is P. In other words, the marginal benefit is constant. Alright? Well, it turns out, of course it's just natural, that the slope of the benefit curve represents the marginal benefit. And because the marginal benefit is constant, therefore the slope is constant. And curves that have a constant slope, we call them straight lines. Alright? So, it is actually drawn as a straight line simply because the slope is constant. This is the meaning of a straight line. The meaning of a straight line is a curve with a constant slope. All right? Is it fairly straightforward? Whew. I'm not done yet. So now we have to figure out what's going on. All right, so what is this representing? Is this representing profit or loss?
Loss.
No? Profit? Come on. You.
Cost. The cost of producing.
No, the difference between the two curves. All right, so this difference here,
It's minus net benefit, or
it is minus net benefit. So a nice way to call it, as a businessman would, is just a loss. It's just a loss. And instead of saying minus, we call it negative net benefit. In other words, the net benefit is negative, which is a different way to say that the profit is negative, but negative profits in business we just call them losses, all right? So early on, and this is the illustration which I was saying is with 5, 10 students, of course 10 students won't be able to pay off for the building, for the heating, for the depreciation, for the personnel, and for maybe 5 professors teaching the courses. They just won't be able to cover the cost of salaries, all right? Or will barely cover the cost of salaries. Now, let me jump quite a few lectures ahead. We call this break even. Does this mean you're second year too? No? All right. We call this break even point. In other words, over here we were running losses. The maximum loss that we attain is wherever the two curves are most distant from each other. So over here we draw it like this, and maybe this will be the biggest loss, or maybe this will be the biggest loss. Well, it turns out that the distance is farthest where this curve, the slope of this curve, equals this one. Let's try to explain this. I'll delete it off so that you can actually see things. Because a lot of times, if you don't see it, you don't actually get to understand it. Alright? So, let's try to draw now a curve which is parallel to this one. And that curve will give us a loss of 1. So, I'm drawing here with a little red. This curve here, right? So, all the way along this curve, we are running that much of a loss. Is that fairly straightforward? Alright? Does it make sense? Is it logical? Now, suppose we want to increase the loss. If we want to increase the loss, what we do is we shift further out. In this case, further up. So, we shift some more. Now we guarantee ourselves a larger loss as long as we're up on this higher curve, alright? And the loss is presumably twice. And of course, now we do this exercise again, a third time, and you're guaranteeing yourself an even larger loss as long as you can get along this shift curve, right? So eventually we'll get over here. And if you're over here, you know in this segment that you're going to be getting even higher loss than over here or anywhere else. So eventually we shift to the point where this parallel curve, in other words, a curve which is parallel to the original one, begins only to touch. And when it touches always in exactly one point. So the point where the straight line touches the curve is called
maximum loss.
No, in mathematics it's called tangency. Tangency is the point where a straight line touches a curve. Alright? And the point we call tangent point. Alright? So, the point of tangency will guarantee you, so I'm just making here a really big circle for those on the back to see it. And this circle is, I want to represent the center of this circle, is the point of tangency. And the point of tangency represents the furthest out from the benefit. And the furthest out above the benefit will guarantee the highest possible loss. Alright? From this point on, so the highest possible loss will be this one here. This is loss. In other words, we're going to be running the biggest possible loss probably with 5, 6 students. And it makes perfect sense. Alright? Now, you have to understand, I'm drawing everything backwards from over here, right? Do you notice this? For those of you who are prepared. Now, over here we're beginning to break even. This simply means that with 21 students, the program is barely making enough money, meaning it's barely bringing enough revenues to cover the cost of heating, cooling, professors, and an army of bureaucrats, right? So, from this point on, the program begins to make money. Each next student costs fairly little, and the benefit is still as large as before. So, we bring here some profit, but if you have one more student, the profitability will be higher. Profit I'm using exactly as net benefit. So, let's write this out here. I can say that net benefit, which is equal to total benefit, equals total cost, is the same as profit. When the number is negative, we call it a loss. How do I write this out? I say profit if net benefit is non-negative, and loss if net benefit is strictly negative. In this particular case, we can say zero profit. Alright? That's a possibility. That's how we say it. Alright? No profit. Is it fairly straightforward? So, now we're moving on, and the logic which I just applied here begins to apply just as well over here. So, I have to draw up the line, and I do. I begin to use now, well, I can still use red, right? Dot, 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 dot. I'm moving further out. The furthest out I can move, the higher will be the profit. And ultimately, I get to the point of tangency. Alright? You know where tangency comes from? It comes from tangere, which is Latin and stands for touch. So it simply means where the straight line touches the curve. Oh, by the way, I set over here, as it is over here, one and only 1 point. How do I know it's only 1 point? What ensures that only 1 point is the tangency? How couldn't we just have 2 tangency points?
It's a curve.
Alright, it's curved, but that's not good enough. Here is a curve, right? And this curve, here is a line, and I actually was able to generate 3 tangency points. And if I use the tangency curve, you know what's a tangency or sine curve, right? The sine curve, I can generate infinite number of tangency points. So, number 1, it is curve, but it's not just curve. Number 2, we call it smooth. The curve is smooth. So, it is the smoothness of the curve. That's number 1. And number 2, the curvature. The curvature all the way along is from this point on, somewhere over here, is concave, all right? And over here is convex, again, depending whether you look from the origin, from below, or from above, all right? So, concavity combined with smoothness guarantees one and only one, meaning guarantees unique tangency. Now, smoothness is usually guaranteed, but that's way too much math, by differentiability. So, if the function is differentiable, it's just elementary calculus, it follows that it's smooth. If it's differentiable, it means that a slope exists, all right? Remember, what's the definition of a differential? This is too much math? You don't need a math? All right. Let me spare you the math. All right. So, the point is, as long as it's fairly smooth and the curvature doesn't... See, here it changes. Convex, concave, convex, concave, convex, concave. All right? So, it doesn't change. In this particular case, you see we have a maximum of a loss and a maximum of a profit. And for our MBA program, I have no idea, but my intelligent guess says 60 to possibly 80 students would be quite optimal. Usually many programs in the world, for whatever reasons, institutional, usually find optimality to be between 80 and 120 students. So my expectation is, seeing what I see here, that the optimal solution for this MBA program will not be too far off from the optimal around the rest of the world, all right? So, this here will represent the optimal solution. This is the one and only solution, as long as, you know, the curve goes higher and higher, doesn't change yet again its curvature, all right? Fairly clear? Whew, let's see what else I have. Well, the way they have done this is they have actually redrawn this difference over here on the horizontal. Now, if you have questions, again, you can feel free to ask me questions.
Sorry, I just asked about the tangible point. This is the most profit they can...
Yes, yes, this is the profit, this is the point. Yes, the ultimate, yeah? The ultimate, yes, the maximum. So, the optimal solution is this one. This happens to be the maximum loss that is attained at possibly 3 or 4 students. And this is optimal possibly at 60 or 70 students. This is the maximum profit. Of course, the idea was the university could choose anywhere from 100 to 1,000, or just 1 or just 2. But the optimal, given the cost curve, is 60 or 70. Let's make it 66, all right? For example. So, let's see what else. Yeah, I can now draw this as a separate, in other words, the profitability I can draw as a separate curve. In the separate curve, let me see how I'm going to do this. I'm going to do this on the side. And I'm going to begin right here. So I'm going to use the same curve over here. So early on, the fixed cost says that we're going to be having that much of a loss, correct? That much of a loss. The loss will be increasing over time. If this point here is P, so what I'm doing now is match this curve to this chart to this chart. Over here where they have the maximum, I call this point P prime, and P prime is corresponding to this P. Then we're going to have this Q, and Q will be up here. So this Q point is this break-even point that you're making neither a profit nor a loss. A different way of saying is that your revenues cover your cost, so total revenue equals total cost, which means the net benefit is 0. So Q is equal to Q, PQ, the next one is R. And of course, we're going to be moving up as to R. The maximum here is R. And this is Q prime, this is R prime, this is P prime. And then, of course, over time it will fall, and eventually, somewhere far outside the board, it will move back into the negative territory. So, the optimal solution, of course, is R over here, or, which is the same R prime as R prime. Now, this curve we call, has two names. How do we call this curve here? Yeah, this curve we call the net benefit curve, right?
Yeah.
And in business, it is called profit and loss, P&L curve. Profit and loss, P&L curve. All right? It's fairly clear? Let's see if I have anything important. All right, so we call Q, sorry, my mistake, R, optimal level of activity. And as a reminder, optimal level of activity was 66, right? This is what we had, right? 66. So this is called optimal level of activity. Let's say marginal benefit, marginal cost, 1 unit, everything's fine there. This has been all covered. All right. So, what is the principle for optimization? For those of you who have a textbook, possibly the same edition, this is on page 91 in the middle. So, the principle is this: we continue to increase. We continue to increase the activity or the quantity as long as marginal benefit is higher than marginal cost. Alright? In other words, as long as the slope of, let's say, the slope of the total benefit is steeper than total cost. Alright? In other words, if each unit brings us extra net benefit, alright? Simple as that. So, a third student and fourth student, we're actually running bigger losses. Then the fifth student brings a net benefit. In other words, it cuts down our losses. A sixth student cuts down the losses further. Seventh unit cuts down losses further. Then at 20 students, we don't make profit, we don't make loss. But the 21st gives extra benefit, net benefit. In other words, the net benefit is higher than the next loss. So, we continue to expand all the way to 66 because each new student, the marginal cost of the new student is lower than the marginal benefit. Somewhere over here at the number 66, each new student begins to cost more, suddenly a lot more. And because it begins to cost more, we will stop accepting more students to the program. Alright? It's just perfectly natural. Is it clear? Alright.
Excuse me, it's a rule for all business.
Hmm?
It's a rule for all business.
Yes, it is a rule for all businesses. Without exception is you expand the quantity up to the point where the marginal benefit continues to exceed the marginal cost. For all, this is a universal rule. In other words, early on, some things may happen. You know, you can't just produce one car. And one car producing is terribly expensive. Just like in Bulgaria, you can't just produce one barrel of oil. I mean, how do you, what use buckets? You know, the first barrel of oil is terribly expensive. All right, it's the most expensive barrel of oil we'll ever have. You know, the second barrel is fairly cheap. You know, you just get another barrel, fill it up. You know, maybe the 100th barrel of oil, you automate a few things, becomes really, really inexpensive. So the point is, aside from the small quantities, you know, of opening a brand new school, of opening a brand new kindergarten, where you got to hire possibly a teacher, possibly a cook, possibly, let's say, a room or 2 rooms, you have to advertise and whatnot. Early on, the first couple of customers, or the first couple of cars, or the first couple of barrels of oils are extremely expensive. We usually don't consider those. You know, we usually consider once, you know, things get going. In other words, the MBA program is running. We've got 15, we've got 20, and then we say, when we acquire, meaning admit 1 more student, will the net benefit exceed the net cost? And the next one is, we continue to expand the quantity, or admit more students, as long as the net benefit exceeds net cost. It is always the case in the real world, due to some physical considerations, like we got 4 rooms, right, and 6 or 7 professors, that at a certain point, costs will begin to rise in a steep manner. In other words, marginal costs at one point begin to skyrocket real fast, all right? From that point on, it doesn't make sense. So, up to that point, it makes sense. And that point is where marginal revenue becomes equal to marginal cost. In this chart here is wherever the parallel to the marginal benefit is tangent to the cost curve. All right? It's the same thing. Is this answering your question?
Yes.
How about if we make a break?